Welcome to our September 2021 issue or edition of PickMy Brain. Unfortunately, when I recorded the Zoom session, I failed to record it right at the beginning. So what I've done is edit a few pieces in and have added this welcome. As you all know, we've been getting increasingly disturbing news from the IPCC about increasing global warming challenges. At this juncture, it's critically important for us to be sharing information from as many places as possible, both successes and failures. And so when John Glassmire, who's a senior advisor for Grid Edge Solutions at Hitachi ABB, and I were talking about this session, he suggested, well, maybe we could take a look at what's happening in Australia. They've been working on a lot of cutting edge issues and had some successes and some challenges. And I can bring in one of my colleagues, Juergen Zimmermann, who is Business Development and Technology Manager down in the Darwin area. And so what we have that follows in this conversation is a recorded session between myself and the two of them, and I hope you enjoy it a lot. Thanks for watching.
My name is John Glassmire. I'm a senior advisor in Grid Edge Solutions for Hitachi ABB Power Grids. And in this role, I really seek to help people understand the value that you can get out of grid edge technologies, including battery energy storage systems, microgrids, distributed energy resources or DERs, and serve a role both internal and external to try and help that happen. I also am fortunate to serve at the University of Washington as affiliate faculty, where I lead a course on distributed renewable power systems, and pleased to be here to share some of what I've learned and hopefully learn a little bit more, continue to learn more from Juergen about what he's learned from what they've been doing down in Australia.
My name is Juergen Zimmermann. I work for Hitachi ABB Power Grids, and my role is Business Development and Technology Manager. And really in that role, what I do is I connect customers to new technology and try to work with them through the application of the new technology into their specific needs. I've been looking at this for about 30 years now, starting with, off-grid microgrids in Australia, working in remote communities, and then really starting from there to transition to the grid edge, where we see the same issues occur of how we connect in renewables, and now working on the main national electricity market to help make that transition there as well. So great to be in the program and looking forward to have a conversation.
So you hear a lot about what's going on down there. Sorry, I just remembered to record. I was so busy looking for it.
Yes.
One of the stories I saw recently was that in one of the what do you call them, states?
States and territories.
It was South Australia, where the Q1 of this year, the electricity price from 10 o'clock in the morning to 3 in the afternoon on average was negative, I think, $12 Australian. And I thought to myself, that is a whole heck of a lot of solar saturation. What's going on down there? Big picture. What is happening in Australia? You mentioned there's a lot of different things, but what is happening? You hear about Tesla's big battery down there, big plans for hydrogen. What's going on, Juergen?
Yeah. Good, very good question. And look, let me just start first, with the East Coast, as we call it. So from the East Coast market, this is really the interconnected market of most of the states in Australia. So this is South Australia at one end. And if you remember sort of the shape of Australia, you've got one end, which is South Australia. It goes through Victoria, Melbourne, Sydney, up the coast via Brisbane to the top, of Australia, as in Cairns, and then the Cape. So that's all interconnected, with most people, of course, living on the coast or close to the coast. But South Australia is quite unique. It's unique because it's kind of end of the line, even if it's end of the line as a gigawatt system, but it's still end of the line. It has got two interconnectors, and the two interconnectors that connect South Australia into the rest of the network are part of the question, how can we now, with lots of renewable energy being generated in South Australia, which is wind, predominantly South Australia started very early with very good wind resources, built lots of wind farms, and they started to export wind into the rest of the NEM. That's sort of about 10 years ago, 15 years ago. Now, in the meantime, of course, what happens then is then lots of solar, as in rooftop solar, came along as well. And a lot of the power plants that were in South Australia, so these were gas or coal, started to retire because there just was no need anymore from an economics point of view. So South Australia suddenly became the forefront of where on the larger scale system you could see the impact of, I think you mentioned in the last conversation, PKD, is this duck curve, where we see in the middle of the day, of course, lots of renewables pushing in. And of course, what happens if you can't export those renewables out through those interconnectors, which are meant to, of course, be an importer rather than exporter, then suddenly those prices will start to drop. So that's fundamentally the story. And the prediction was that this would only happen, 5 years from now or 3 years from now, when we see these negative prices for extended period of time. Suddenly all predictions around this take up of renewables, they're all wrong. Everything happens faster. And hence we are in a situation now where, from a planning point of view, South Australia is now looking, saying, well, what can we do, right? And there's really two things that they are doing now. One is there is now planning in place for a large interconnector to go across from South Australia back into now New South Wales to be able to export more. So for them, it's all about exporting. But at the same time, South Australia has also done well in the sense of planning ahead for their state and putting some extra requirements in place around inertia and what they need in order to operate that state when it islands. Because it does happen that this state islands away, and that really means suddenly you have this large isolated system that you have to operate on your own without any interconnection to someone else. So that's really what's happening in South Australia now. They're at the forefront when you see of the issues we face down the track.
Okay, now you mentioned the word inertia. I would venture to say that if folks are anything like me, I only understood what that was 2 years ago. And
right.
if I can explain it, I'm going to parrot what I think it is, which then everyone here will go, okay, that makes sense. And then you can tell me if it's wrong. Okay, so in the power grid today, you need to manage the quality of power and the frequency, the 3,600 RPM and in the generation plants that they're typically spinning at something like that in a 60 hertz system. And they speed up or slow down to manage the frequency on the grid. Am I right so far?
Yes, you're right so far.
And that inertia of the heavy spinning masses of metal is how that phrase came about. Now, we start to reduce and remove those large spinning masses of metal, the coal plants, the nuclear plants, all the steam generation. And we're bringing in wind and solar that don't have these heavy rotating masses of metal. So now we have to find other ways to manage the frequency on the grid. Am I right so far?
Yep.
Okay.
Yep.
Now,
great.
to do that, we either bring in batteries or smart inverters, or now you tell me, explain to me what is the thing that jumps in and takes over and plays that role of managing inertia on a go-forward basis. This is where you can explain it way better than I ever will.
So do you want to jump in, or you want me to jump in?
No, you go, John. You go.
Okay, yeah. Fine. So you said, what do you put in there? Well, you've got some choices about what you can put in there to try and keep, the ultimate goal is to keep that frequency right where you want it, right in the middle. Here in North America, we're looking at 60 hertz. Down in Australia, they're looking at 50 hertz.
50 hertz.
Obviously inverted because it's the other side of the world. I won't make too many of those jokes.
And the whole thing hurts.
So they're doing 50 hertz, but it doesn't really matter. And historically, there's been the turbines, be it a gas turbine or a steam turbine nominally that does this, or in a lot of fortunate markets, a hydro turbine where they are spinning due to the water. But the new kid on the block, really, and even though Juergen's saying it's established technology.
Did you guys say the same one, or was it me?
It was you,
sorry. Yeah. The new kid on the block.
Yeah, so the new kid on the block in the scope of our 120 years of history running a power sector is inverters. And specifically, the big one we're really looking at is battery energy storage system inverters. And they have, through a feature that we call virtual inertia, they basically go and mimic the behavior of these and then provide those services to try and keep that even though it's not actually spinning something, we're simulating it. And frankly, it behaves the same if you do it right, and actually is better because it's a more flexible asset. So Juergen, you add on to it because I know you've got some unique takes.
Oh, look, I mean, fundamentally, yes. I mean, it's so what's the new kid on the block, right? And what we've done, and I go back a little bit in history here, right? Because we had to solve this issue about 15 years ago the first time, right? And no one at the time believed that this is of any significance, but we thought we needed it anyway, so let's just do it. So why do we need it? And it's very similar to Alaska. Of course, Australia's got a lot of off-grid systems, remote systems, and that's where the driver to change to renewable energy away from diesel was always about cost reduction and this resilience to be independent of the fuel truck coming in. So people ask us all the time, well, what can we do now to increase renewables? It was mostly wind at the beginning, then solar came in as well in those remote off-grid communities. And we thought, well, there's got to be a way how we can turn these diesels off, right? Don't have to run them anymore. We want to turn them off to maximize the amount of renewables we can put in. So at that time, inverters came, of course, about, everyone, first inverters, if you go back a little while, they were drives, right? They were used for drives, right? As in to run motors and drives and stuff. So then they were used also for solar first, and then they, of course, were used now for batteries. So when we used them with batteries, and at the time we used lead acid batteries, again, this was a while ago, then we said, how can we now make this inverter from a software point of view behave like a generator, right? All we want to do is we want to make it behave like a generator, because if it behaves like a generator, it does everything that a generator does in the system. And because inverters can be software driven, and I think this is from an academia point of view, this is a very important topic. Once you look at it, how you can make things work through software, your degree of freedom of what you can do with it is enormous. Meaning if you do it well, you can actually do better than what a generator does. So this story actually emerged in the off-grid systems, where we then first solved this issue, how to run an entire township purely on solar and inverters. And those inverters, we put software in that then mimicked the behavior of a diesel generator. That's how this all started. But we solved the issue. We solved the issue at that time. And then really since then, all we've done is scaled this up or made this work with other parts of the system. So fundamentally, like John said, this battery system that behaves like a generator, it uses what we call virtuous inertia, but fundamentally it just pushes current out. It pushes current out in a certain way, and the way it does it is it does it the same way like a generator would do. And people call this a digital twin. We just call it a virtual synchronous machine, but fundamentally we managed to do the same and prove this now. And this is coming back maybe step forward into South Australia again. It was a matter of proving that this ability to run this inertia piece on the network actually works, because no one believed us, right? So I think this is one of those steps that we've managed to achieve now in Australia, is to say, we are able to run a 30, 40 megawatt battery system connected to this national electricity market, and it does provide inertia, and we're able to measure it, and we're even able to measure it and demonstrate it works better than what a conventional generator does. Why does it work better? Very simple. If you look at a generator and you look at one of those frequency drop events, and I use the example of the parachute versus the anchor. So if you got a normal generator, right, and you got a normal generator and frequency drops, so the inertia piece is like a parachute slowing things down on the way down, right? However, if you then try to pull frequency up and you've got this generator with all this heavy metal, it's like an anchor, you're trying to drag up again, right, afterwards. So it's very difficult actually then lift frequency again, where in a battery system, you can do the slowing down as well, but you don't need the anchor drag anymore. You just don't charge it. You just wait, right, until the frequency is stable and you've got the luxury to do it. The second thing is, that this parachute in a conventional generator, because the mass is always the same, is always the same parachute. You can't slow it down more or faster or more or less. Where in a battery system, you can actually change the software, you change the parameter, and it's adaptable to what you need at this point. So cut long story short, this is really one of the pieces, being able to provide inertia into a power system from a non-rotating piece of machinery. That's been the key for people to see now. This is actually possible. We can take generators offline.
Excellent. I've got one question. We're going to drive inertia into the ground. Okay.
I want to add something on this, though,
okay.
But go with your question. Okay. I want to circle back to this.
Here's the question. All right. I get that big picture level. Now, though, you have Australia with what, 2,000 rooftop solar arrays. Yeah. And so now, and more batteries behind the meter. Does inertia not only have to be managed sort of at the grid level, like the utility scale, like you're talking about with large batteries, large power plants? Are we now having to migrate that management all the way down to the local feeder level neighborhoods, that sort of thing? Is that the next step?
Okay, to answer this from a power system point of view, inertia, right, is across the system. So you're right. The inertia piece can be managed across the system, but, and I don't know if you've come across the term that's called system strengths, which is around voltage and voltage needs to be always managed locally.
Mhm.
So this is now one of the ones that we're solving now. So we solved the issue of inertia. That was about 3-4 years ago in the large name system. The question now is, near IPKD, what do we need to do to solve locally the issue of lots of rooftop PV pushing in order to make sure that power system is still stable? But we come to that separately. Let's just finish the inertia piece first.
Okay,
So,
great.
so there's one key element around inertia. So when you think about inertia, what is it? Inertia is an inherent property of something, right? So you think about all these, going back to your initial, why do we have inertia? You have these big spinning masses, right? Well, what's the inertia in the system? It's a description of that mass, right? That mass spinning is the inertia, and that's an inherent property of that thing. It's inside and intrinsic, right? So if you look at, say, a lot of the other inverter-based generation, you know, these things like solar and wind, and in fact, a lot of the battery energy storage system, they don't have this inherent capability. The way they mostly operate is they look to the grid and try to snap onto it and then inject power strategically in line with it. It's called load following or grid following, right? And so you can do a certain amount of keeping that frequency right where you want it to be with that by just looking and listening. But eventually, if you don't have any inertia to look to follow, or any frequency to follow, you then have to start leading, right? So you move into this space of taking inverters that form a grid and can actually provide that inherency. And so there's a distinction between most of the electronics that are out on the network today in the US and even in Australia that don't have this grid forming capability. What you need is, when I described, you know, how these work, they have their own little model of this inherency of the, you know, they have a model of the generator spinning. That's inherent to the thing, inherent inside the power electronics. They have that, and that ability to essentially lead and cooperate with others while cooperating with others is key here. It's that is a technological leap in the mainland systems that needs to be done. And that's part of this element of inertia, is it's having the ability of new things coming on to provide that inherency through the way they interact with the network. I don't know if does that make sense?
It does. I'm going to ask a follow-on question that I think might help.
Yeah.
Okay, so we're talking about managing frequency with this inherency.
Yep.
Frequency is the oscillation, right, of current with in X number of seconds. 60 hertz is 60 oscillations per second. Is that right?
In the US, yes.
Yes, and 50 in Australia, or half of Japan and not the other half. Okay.
Right, exactly.
Yeah.
And if you drop below certain frequency levels or exceed them too much, now you have the possibility for what we almost saw in Texas, where an entire grid goes down, right? I mean, why is frequency important? Please explain that to the audience.
Well, everything's geared around assuming that we're at 60 hertz in the US. And so if you're not there, everyone is just sort of implicitly assumed we're going to do it. And if you're not, havoc ensues.
Because what, the machines can't take that oscillating power at a different frequency?
So the machine, so the synchronous machines can't handle it. They would be struggling against it. There's it's baked into the way the system protects itself. There's a whole section of the grid. It's somewhat of an art form that's just based around standards, where all of this protection, or what they'll sometimes call selectivity, is geared around this being near that frequency spot. And if you get off of it, then the grid can't protect itself. The power doesn't translate well where it's supposed to go, and the generation can't feed in. It just falls apart.
Excellent. Okay, that's very helpful. Everybody good with that? Okay, so what's the next piece then that happens after Juergen, we figured out how to do this for isolated grids and then bring that into larger scale grid? What's the next hill we have to climb here?
Okay, so let me just order and explain, because I had other network operators and asking me, okay, once I've got these, inverter-based, say, inertia machines out there, I mean, how do I control them? I mean, how do I actually make them all work together? And the answer is very simple. It's the same what you do now. right? Because the principle is we're just replacing an existing generator with one that's based on an inverter system with the software making it look the same. So their concern about, well, how do we make this all work together is actually very simple. And that is you dispatch and you can control them the same as you do at the moment. And we see this unfolding now when we are going through, say, a quick connection process, right? Where you just have to, of course, do all the modeling and stuff like that. But then the actual connection back to the operator and the dispatch signal that they do for a large, say, gas turbine or coal-fired power plant is the same that we would be getting as well. So the integration piece at the end of the day is not that complex. Of course, there's a little bit more to it as the network gets more complex with more different generation and resources, but fundamentally, you can do it the same. So let's look at the next challenge that's not coming along. And that is as you push more and more renewables into those networks, and like you said, PKD, what happens now on the distribution level? What happens on the level of, the, say, streets or other parts where we suddenly see, potentially what's called instability around voltage? Now, maybe for the audience as well, we talked before about 60 hertz, is the frequency 60 times per second, how the sine wave, how often it actually swings around. But then voltage is really about the amplitude, as in how the amplitude of the sine wave and its quality. How well is it actually defined, right? If you think about a line, you can do a line that's very thick and very strong, or you can make a dotted line, right? That might not be so strong, or you might have one that's a bit jittery, right? That's not so good either. So it's all about, like John mentioned before, this reference signal that interties everyone, which is around this sine wave that everyone looks towards to make sure we are working well together as all the different generation, but all the loads together. So what happens when this sine wave is not so good anymore? And this is not about how often it swings per second. It's purely about that its quality might not be so good. And that can happen, when we are removing lots of the generators that have been forming the sine wave. And the issue is the further a device that wants to connect to this network is away from a generator, the quality of the sine wave can actually deteriorate. When the quality of the sine wave deteriorates, the ability to connect to the sine wave deteriorates as well, and we see more and more solar or wind potentially dropping off. And that's what's happening in some parts of the network now. And the terminology that people use around it is system strength. System strength simply means how strong is this point of the network represented through having enough generators close by to make this point of the network really strong. If it's not very strong, it means renewable plant that want to connect are challenged because they can't see the sine wave so well. So what do we do and what does that actually mean? So what it means at the moment is that, and I first start maybe again on the larger scale and go down to the smaller scale. What we see now in Australia is in a specific region in Australia where this has played out quite open, and that is the best resources of renewable energy, as you know, it's wind or solar, are in regions of the country where the network is just not very strong, right? And, to build new power lines to connect these things up is usually not an option. So what happens is that you build out along these long lines coming out all these beautiful large solar plants, but then the network connection at these points is very weak, and hence you're very limited how many or how much you can build. And that's where the system strength bit is coming in. How do we now reinforce the network at this point without having to install lots and lots of new equipment, but actually trying to use the existing equipment or, again, battery system to do the same? And that's what we're doing right now in Australia, to work that through to make sure we don't reinstall rotating machineries at this point in order to make the system work better or stronger. We're saying, no, you can actually use again those inertia-based machines. We call them virtual synchronous machines that can provide that same system strength and the enforcement of the sine wave. So I'll stop there for a second.
Okay.
That's really the one we're working through now to allow more renewables to connect, and that's both on the level of transmission level as well as distribution level.
And as the Federal Energy Regulatory Commission just noted in its notice of public rulemaking that we're going to open on transmission, they basically stated, well, variable renewable assets like wind and solar by definition are located far away from centers of demand, because you need space for them. So
Yeah.
it's almost a problem that's inherent in the solution. A couple questions have popped up while we've been talking. One, inertia, the question is, does inertia play a large role in microgrids? And I think you mentioned before that that's where you sort of started to try and solve it in the beginning. We're in those nano and microgrids. Is that right?
Absolutely correct. That's the heritage. That's where it came from.
Okay. And then another question, is there inherently anything worse by being over or under the 60 hertz or over or under the targeted 50? Is it worse to be above or below, or are they both equally as bad? If it's 10% on either side, is that just plain bad?
I have it answered. So below is worse than above. The reason is very simple, right? You can always quickly get rid of generation when you're too high. So of course, if you're above, it means you're generating too much. When you're generating too much, you're speeding everything up and everything gets basically to higher frequency. It's always easy to say, get rid of this generator very quickly, right? Excellent. On the other hand, if you go down, you can't bring easily new generators on, or you really want to avoid cutting customers off. So that's why going downhill is always a lot harder to catch and going, back up again.
Excellent, Annie. So far, you win the prize for best question. So congratulations. Because I was thinking, it's probably the same. Another question here: what is the cost of losing your grid or site power? Olu, can you jump on? Are you still on? Yeah. Do you want to actually ask that question in person and amplify on it?
Oh, yeah. I heard grid forming technologies, right, for inverter-based systems. So I was just curious I didn't know if the price point was something where it's getting cheaper now, right? Or maybe the future is looking like it's going to be more standardized to be grid forming as opposed to grid following inverters. That's kind of, what the perspective I was asking. Yeah.
I'll jump in and then Juergen. So I think it's here in the chat. The question around framing it exclusively around cost is fundamentally the wrong way to look at it, because you want to look at the value that it affords you, the value that it provides. And if you're in a network, I don't like using the word weak or fragile to describe a network that's not strong, but you're in a network that doesn't have enough strength, then the value of a grid forming inverter goes way up. So the fact that it may cost a little bit more than a grid following inverter, not really the right question. Certainly, it's always a good idea to be as economically efficient as you can be. So it is good for the costs to be coming down. The costs are coming down. The performance is getting better. You look at this, there's trends around, it's a computational thing. There's trends around the cost of the fundamental components. There's more experience, there's more scale on them. The costs certainly are improving, but the need is going up significantly globally.
I think that actually will help me. Thank you very much for clarifying, because if I was going to justify a business case from a developer standpoint, taking out a loan, right, all the costs kind of add up, right? But if I like what you're teaching me by saying just kind of frame it as the benefits, right?
It's a cost benefit analysis. Yeah. If you are trying to get to, let's say you want to plan a vehicle to get to the grocery store every day.
Mm-hmm.
If you look at cost, the best thing you could probably do is buy a new pair of shoes, but you might want to get there a little faster. Maybe you buy a bicycle. It costs a little bit more, but you'll get there faster. And if you really want to get a lot further, maybe you should we're not going to buy an internal combustion engine car, but we'll buy an electric vehicle. And that's certainly more expensive, but it affords more value that you need if you're going to try and do other things in your life.
Understood. Thank you. Actually, thank you.
And then pick up the shopping for the neighbor as well. So, what good question, I really like it, is about, and at the end of the day, this is all about economics, right? And that's just something I learned in my career as well. You can build the best widget. You can build the best thing you can ever think of. You can even have people that support you in this and give you, lots of claps. But fundamentally, if you're not able to convert this into a meaningful business case that would support an investment decision, you got no hope, right? And it's one of the things that I learned over in my career as well now, is to say, we start in these off-grid systems and, we love them, they're great. It's really good to work in them. However, the business cases and the difficulty to make things work in these off-grid systems, because they're very sensitive to stakeholder management and lots of stuff. Very hard to do this there. Now, I learned the same thing now in Australia, but talking to developers. The best lessons learned that you can do is talk to the developer, get the business point of view that is non-technology, to really understand what's on their mind, how do they spend their money. And that's one thing now in Australia we see that has to change, or is changing now, is the value, to recognize the value and pay for the value of inertia, right? The reason is because in the past, these machines that were driven by gas or coal or whatever it may be, automatically or inherently, were just providing the service anyway. So no one had to actually think about who's going to pay for it. Now with these machines retiring, there has been no mechanism in place to allow investment for that to happen. And this got worse and worse, meaning more and more people want to build solar farms, connect, and simply sell energy, because that's where you make your money, by selling the energy. But if you can't connect, or even once you did connect, you were then curtailed because of constraints in the network, everyone gets scared and says, this is too hard basket, I'm not going to do this anymore. So what the regulator had to do, they had to really work out now who's actually in charge of reinforcing the network to allow renewables to connect, because together we all want to make sure we get to zero carbon by 2030 or by 2050, whenever it is. So what the regulator did is to say, okay, first we need a market for inertia, as well as we need to look at who now takes charge of the investment upgrade of the networks. So they created now these renewable energy zones, and the responsibility to enforce the networks in the renewable energy zones, which are dedicated areas that are part of the network where people then can connect, or developers can connect, and they know when they can connect, their cost to connect will be manageable, right? But the TNSPs, or the transition network service operators, they are now the ones that need to look at how to strengthen the networks in these areas to allow the connection to happen.
How do they figure out how to price inertia so that some entrepreneur says, oh yeah, I'm down for that. I'll put a battery there. How does that work?
Yeah, it's a quite good question, PKD. And look, I to be honest, I don't have the answer at the moment. All we know is there will be a value to it. Okay. And this whole thing about what's the cost of a megawatt hour in the future, who knows? You mentioned at the beginning, we're at negative prices throughout the day in South Australia at the moment. I mean, you could have predicted this. And this is part of the bankability of these projects that are run over 10 or 20 years, right? Who's prepared to really take risks? All we know is you will be able to make money in the future. And to a certain extent, by doing now what we're doing with these battery systems, with this grid forming at the front, we know they're going to change. We know new functions, features will need to be done in the future, so you don't have a stranded asset. And because we can, with software, enable more functions, it's actually a good way to secure this asset into the future by allowing new things to be put to it, so it can actually make more money in the future of things we don't know about, because we're going to disrupt ourselves again with new ideas and new ways of doing it.
So we're talking about business models. I get really excited.
Oh, I'm sorry. Oh, sorry. Yes.
No. This is good.
This is not how system works. Yeah.
For those of you that are still tuning into this, I want to thank you first for going with us on a journey spanning power systems, legal problems, economic challenges, all sorts of different things where we're all a little bit outside of our comfort zone of things we might already know, but all are important for making the grid of the future happen. And we're trying to figure out how to standardize it. And there's different approaches that people are taking. That's part of the reason we wanted to say, well, look at Australia. How is Australia doing it here? I don't believe, actually, correct me if I'm wrong, I don't believe Australia has a price for inertia yet.
No, we don't have it yet. No,
it's a regulated service that the wires operator, the people who run the network, are obligated to make sure is there, and they don't necessarily know how they're going to do it at all times.
What is happening now is that the actual, say, TNSP as in the transmission network service operators are going to market, and now they're buying our system strengths, for instance, right? They're buying our system strengths in an auction type way, right? To say, I need that much system strength at this point in the network, who can give it to me best? And right now, for instance, there's a tender out there where you can put this in, and you got choice of technology. You can use this technology or you can use this one, which is really good that at least it opens up, opportunity to demonstrate this on a larger scale.
But this is a relatively new development on the heels of, if I was going to do a renewable plant, I had to bring my strength with me, right?
Correct. Yes. In the past, if you want to connect your renewables, you have to bring your own piece of kit with it, right, to make sure you stay online and you're very connected. And if everyone needs to do their own thing, it's like John, going to the shop and, trying to buy his groceries. If everyone has to do it on their own every way, it's not so good. But if you actually do it as a combined thing, the cost, of course, go down. But the question is, who does it in the first instance, right? The first guy doesn't want to be slapped. The last one gets all the benefits. So it has to be organized differently. And that's where state governments here stepped in and said, we're creating these renewable energy zones, which are dedicated areas. That's where you can connect.
And if I can, I don't know, is it okay if I take us on a little bit of a tangent, PKD?
Why not? We've looped around a couple of things already.
Good.
Please do.
Good. So if you think about, so the story of the past 40 years globally in energy markets, what would you say is probably market liberalization, right, PKD?
Yeah,
the idea of So the idea has, we've spent the past 40 years trying to figure out, where can we allow competition? Where do we need a monopoly because it doesn't make sense? And trying to set up all these rules in an already conservative industry to try and standardize this. And so now we're showing up with a technology, a battery energy storage system technology, which provides not only these generation services. So, you're trying to compete to sell your energy. There's a bunch of people trying to compete to sell energy. Battery can compete there. They can sell the energy and they can sell some ancillary services. But they also, particularly as you get into these networks that have declining system strength, they can also support the network. How do you create a business model in an environment where they've tried to peel those apart and say, you can do the network and you can do the generation, and all of you can try and do this generation, but now we have a technology that sits in between them and is a linchpin technology for meeting our energy goals. That's just, it's a wildly exciting regulatory challenge. And that's part of the reason I like to look to Australia, is that they've been navigating this. You look at, say, the, I don't want to, I'll pause there because it sounds like people want to chime in.
John, you brought up a good point, because that's what we're dealing with in ERCOT in Texas. I'm based in Austin, and I saw this perfect storm coming a long time before February. And that's just it. Can we have private use networks that can bid into any type of exchange, blockchain or whatever? We have and then we have co-ops and municipalities. They're still struggling to make the decision to switch because they keep their jobs if they don't make a decision. And so it's actually a lot of fun. But I really love the dialogue that you're putting together, because I do look to Australia, I look to Germany, I look to Hawaii sometimes, and I think the other bottleneck that we're really looking at is the role of contractors and utilities, and to really get the commissioning process handled universally. And then especially Texas is ERCOT's non-FERC, so we're not gonna do Order 2222 and it's all way. We'll do it in the Wild Wild West way. Who knows how it's going to roll out? But thank you for bringing that up too. And I'm really excited about what you guys have for the grid edge solutions coming out, because it really is that edge of the microgrid and how you define that.
And it's really moving. So the way I see it is actually moving. We'll talk about off-grid systems first. This is where they started. This was a need was first, and we solved the issue first. From there, it now moved to the edge of the grid. Right. And again, it's all about business cases. It's all about justifying the investment. Why the edge of the grid? Because that's where the networks have interruptions. People get, disconnected. Hence, utilities have a strong case. So, and that's really maybe where I might just bring in now this ESCRI example that people, have sort of referred to, which is in South Australia, which is actually a battery system at the end of a long transmission line. Now, that's a 30 megawatt battery system. And why was it installed in the first instance? It was installed, and I've got to get credit to a guy that probably none of you heard of, but that's okay. His name is Paul Evert. He worked way back, in the Western Power, Western Australia utility, he built all these off-grid systems, and he saw, unless we demonstrate technically that this stuff is happening, it's a chicken and egg thing, right? Unless you demonstrate technically it's happening, no one's going to do it, right? No one's going to pick this up. So he said, okay, we need a bunch of money. This was supported by ARENA, which is the federal government agency that looks after renewable energy grants. It was supported by ARENA. And what it did, it demonstrated that on a transmission connected battery system is able to do multiple things, 5 things it's doing, right? When it's connected to the transmission network, it's able to provide this inertia. It's able to trade. It's able to also manage power flow across the transmission line. But what it does really well, and it's one of the reasons why they installed it at this point at the end of the long line, is when the line goes, and the line does go, it just happens 9-10 times a year, people are without power. So having a battery there, and one that can actually inform the grid, it's able to make a seamless transition. If the line goes, who cares? Doesn't really matter. We still have power to consumers. And suddenly all the benefits from this, people realize, well, what can you do with it? And suddenly the linesmen realize, well, we don't have to work at night anymore because we can only have an outage at night to work on the line. They can actually do their job during the normal day now because we can just turn the line off and who cares if it's there or not. We can actually still supply customers at the other end. So one of the things we realized, once you install technology like this, you then actually see multiple benefits that other stakeholders didn't see before. And so that's the starting point to demonstrate and create certainty that technology is there, but the business case now needs to follow. And I did develop an appreciation much more for people that come up with innovative business models, right? How can multiple stakeholders benefit in a way that revenues get shared from this one asset, and how you pull this together? There's innovation that needs to come from this space as well, not just technology, to unravel this regulation and all the dependencies we have in this market-driven exercise.
So some of you Juergen said ESCRI, and you may not have known what on earth that is.
Oh, sorry, yes.
I typed it in the chat. It is a mouthful, and it came out of an Australian government program, so naturally it has an acronym. Every government program must have an acronym, and this one, the one they chose, is ESCRI, which it's energy storage. I can't even remember what all the. Do you remember the whole acronym? I know the SA. That's South Australia.
Yeah. And then it's about renewable integration somewhere, I think. Yes.
Yeah, energy storage, something for renewable integration in South Australia.
So you mentioned it's 30 megawatts. What's the duration on it?
So it's actually interesting enough. See, everyone thinks batteries need to be really, really long, as an hour or two. This was actually purposely designed to be very short. It's only 20 minutes, right? Why is it only 20 minutes? Because the services it provides need to be only short. So the inertia piece, this transition to go from grid connected to unended, doesn't need a lot of energy. So it's actually quite a small battery in comparison to maybe other systems that get built with much larger batteries.
You were mentioning systems. One of the things that I've seen a number of announcements on are these virtual power plants that some of the Australian state governments are stitching together, or with incentives or promoting, where they're talking about thousands or tens of thousands of households with solar plus batteries that they will then aggregate and treat as an integrated machine, if you will. Can you talk to us a little bit about what's going on there and what's the state of play?
Yeah, sure. So look, I mean, this is one of those call it programs that have come out of the fact, and we can come back to South Australia. It just happens there, but happens in other places as well. So what they realized is that with so much renewable energy on rooftops coming along, how one can we make more money from it, but two as well, how can we better integrate this into the networks? Now, when we talk about trying to make money from it, when you look at a 50 gigawatt system, which is the national electricity market, and you've got a rooftop PV system on your home of whatever 5 kilowatts, there's no way you can start to make money by bidding into this market and you become a trader, right? So the fundamental idea here was that you, of course, aggregate all these different rooftop PV systems into one larger virtual power plant, and then bid the larger virtual power plant, which say could be then 5 megawatts, right, into the national electricity market to make money from it. Normally, you might sell this to a retailer if you got access, renewable energy. But in this case, actually, you don't sell it to a retailer. You sell it, to an aggregator, and then that aggregator actually makes money that way. This is a purely economic piece that's got nothing to do with technical or and other things. So that's how the business case for rooftop PV has also improved. And lately, what has happened as well is with battery energy storage in the home, those have been added to the mix as well, so that it becomes more dispatchable. So fundamentally, all this home-based battery energy storage system got aggregated into, again, a virtual power plant. And then they can, like you said, when it's negative prices, they will charge. But when it's positive, of course, they want to make money and they will discharge. So virtual power plants are part of the solution, right, in regards to how we make this transition happen, because we do need to get better control or understanding and visibility of the distributed energy resources.
Thanks. And those batteries are what I think Generac in this country has 16 kilowatt hours on the high side, and then you see some as low as like 8 kWh. Is that the same sort of range you have there?
Yeah. About 8 kilowatt hours up to 16 kilowatt hours, that sort of size and number is about right. That's correct.
We probably use a lot more electricity here in the US. We're doing 20 and 40s.
I saw a really interesting project. In fact, I wrote about it for Forbes, where there's a developer there, and then the company Sonnen with the little s, lowercase s. And they were working on a housing development with 1,000 new homes. And 3 different sizes, cookie cutter sort of houses. So you get like 20 panels on the roof, or 25 or 30, and then you get 8 or 10 or 12 kilowatt hours of batteries in your garage or your basement. And essentially you paid them $15,000, $18,000 or $21,000 for the kit up front. And then you paid them $40, $50 or $60 a month as a subscription fee. And the customers never saw their electric bill, because Sonnen paid that whole thing. And then they sold the services from the solar and the batteries and optimized the entire economic package. And now they're working on a 5,000 home new housing development. There's such interesting thinking going on down there.
Yeah. And it's like it's innovation around the business model. It's not innovation around the piece of kit. It's really, how do you package this together now in a different way, so the impact of what you're putting in there is much greater. So yeah, you're absolutely correct. That is an important piece now that we need to better understand, how we can make that work.
So just to let's reflect on why someone might install a battery at their house, right? So why would you do that? So if I were to take my traditional economic thinking, I'd look at it and I'd go and say, oh, it costs you 10 cents a kilowatt hour for your electricity. And that's it, right? You pay a connection fee and you get that 10 cents a kilowatt hour. And there's really no benefit to having a battery sitting there, right? Because you have this tariff. They've taken all of these costs and levelized them and flattened them out into your 10 cents a kilowatt hour. Now we have these new things coming out. We have climate change causing fire impacts in California and in Australia. You start having your power go out, you start thinking about, maybe I do want a battery. And it's not even about the money, it's about what value can I extract myself. You're not thinking about it in a way of just making money. And the other element is this ability to do virtual power plants. That's really critical. And in the US, with the FERC Order 222, which I think you probably talked about at length, PKD, that allows you to do, it doesn't yet, it will allow you to do virtual power plants in the US. That is one of the key things that order from the
some areas.
Yes, in what, about half the country.
Not in Texas.
Not in Texas. That's right.
I know.
You're the only area with a market that doesn't get it.
We're gonna figure something out.
And then, but I think it is going to hit about half the country, though.
Yeah,
something like that. Yeah. So anyway, just this is the evolution. This is all around business models. Like the need was there. It's just getting the regulations and the money and the environmental needs to all stack up and make them happen.
Okay, so I have another question. All right, so now you start to do this. You bring in the Inertia you create those interconnection capabilities, you add more batteries to the game. And if you look at, say, the island of Kauai, you're at 60% renewables. If you look at Maui, you're at 50.8%, with 22% of that coming from customers behind the meter. It's pretty clear we can probably get to 60% carbon-free grid with a mix of wind and solar and some storage, and then some really flexible gas gen. But when you finally want to push the gas gen out of the mix and go to that 100% free nirvana that everyone's talking about by 2045 in California, 2045 in Hawaii and other states, how do you get there? Is hydrogen the only answer we know of now? Or, I mean, when you look at this longer term, John and Juergen, what's the long-term game plan 20 years out, let's say?
That's a $1 million question. I like it.
Yeah, you was going to say you need to pay big bucks to get that one answered, you know.
Well, I know in the western part of Australia, in your Pilbara region, they're talking about 20,000+ megawatts of wind and solar feeding electrolyzers to build hydrogen.
Yeah. Okay. Yeah.
Go ahead.
So look,
Juergen,
I'll go first and you can come up. So basically I'll go back to the off-grid systems, right? I mean, how do you get to 100% there? You know, versus how do we do it in the large network? And for me, it's so in the large networks, it's first of all about sector coupling. So when I talk about sector coupling, it just means we need to, of course, electrify as much as we can. Once we electrify, you know, we will be able to get more flexibility into the load, and the load may become to a certain extent, you know, a generator as well. But we need to be able to have more flexibility as to when the renewables, of course, are high, we'll want to then make sure we produce or we move or whatever happens. So there's another maybe 10% or 15%, I don't know, I haven't done the numbers, it depends, of course, is there. But electrification and sector coupling, I'm talking about now transport, of course, e-mobility, that sort of stuff, is a key part of making that happen. But then it's like the last mile in a telecommunication system, whatever it is. How do you still get to the 100, right? And look, that's where, of course, things like hydrogen look promising. And I think, you know, they're certainly part of the solution, but I also have to say there's a lot of hype around it at the moment. A lot of money gets thrown at it. It's unbelievable, you know, if you look at, you know, how many millions. And I say that with all respect, now the big end of town is starting to invest here. So when I say the big end of town, suddenly now the gas companies. The gas companies starting to embrace hydrogen because they know they have to move, they now have to do something. And once they start to do something, it usually happens, and it usually happens fast, but in a way also that it's scalable. And that's why you said in the Pilbara in Western Australia, you've got all these mining companies and oil and gas as well. They are definitely banking hard on making hydrogen for export or for their own decarbonization of their own operations. And I think that will be the important piece to get to 100%.
So I think this was geared around hydrogen specifically, right? So there are some,
or just in general, how do you get, you know, all the way there? And what are the lessons from Australia on that?
Yeah, so you mentioned Hawaii. You have to be careful when you talk about renewable. Hydro is cheating.
I know.
Because hydro makes it easy. I mean, Australia has Tasmania.
Yes.
Hawaii has Australia. Here in Seattle, where I am, we have BPA. You know, and that makes it easy. I get 90% of my energy renewable because of the hydro.
Yeah.
So, but there are large chunks where you don't get a large spinning mass that produces renewable energy. The question becomes, well, how do you do that? And I think it's clearly very, very likely to be wind and solar are going to keep pushing in. We're going to keep taking off these other things. And then you get into, okay, I mean, I think the first thing, and this is the lesson is, you have to be able to get to 100% before you can get to 100%. So that's a confusing statement, of course. But what I mean is, you have to be able to operate 100% on renewables for at least some part of the time. It's simple math, right? So if you think about which I don't remember which of the algebraic theorems is, you know, there's a bunch of them as you go up the ladder. But you know, if you're going to try to get to, say, 50% renewable from excluding hydro, you are then when the sun shines maybe, you get about 6 hours of sunlight a day, something like that, peak sun hours in the sunniest spots on the globe. So there are 18 hours remaining that have to be fed from this resource. And that means you're going to have this ability to completely turn off everything, at least in the middle of the day. And the idea is you'll get there first, and then you'll start pushing and pushing it out. So in the remote world, we'd call this, let's go diesels off. And that was what Juergen was talking about. You got to stabilize the network. You got to have this alternative to diesels, alternatives to synchronous generation, to turn those off and stabilize it. And that's, I don't think we've pushed that anywhere on Earth far enough as where we need to go, except in some of these remote communities, even in Hawaii. So that some of those areas is getting that stabilized. And I think when you start looking at, say, something like hydrogen, which I think optimistically people are saying it's going to be ready in 10 years, and pessimistically, who knows? But the first thing we're going to do is, just like we've always done when we start looking at energy problem, is you produce energy even if you don't need it, and just so you have it when you do need it.
Yeah.
And
overbuild, maybe. Yeah.
Well, I mean, so it's not, this is, I take issue with calling it overbuilding.
Okay.
From a certain perspective, it is overbuilding. But if one of the beautiful things about power is that it's available when you want it. If it's not available when you want it, it loses a lot of its value. And so if you overbuild to allow you to have energy when you need it, power specifically when you need it, that is a good thing. So I think we are still in this area, long duration storage, things like hydrogen or pumped storage, or some of these new fancy chemistries that people are looking at in batteries. Those are still a ways off. We still have a lot more mining to do around stabilizing a network and operating 100% on renewables for extended periods of time. So just sort of crystallize some of this. And that's something that Juergen taught me really well. I've been working with Juergen for many, many years. That's something I've learned from him. So I do, the first key before we even talk about long duration storage is getting a stable network.
Yeah, it's very similar. We said stabilize first, then store, right? Because the storage piece is an energy piece, and economics to a certain extent will solve that for us. If the incentive's there, if it's a drive towards a lower cost to store energy, people will make investments that will come, but they need a call it platform, that they can connect to. If that platform's not stable, it's not regulated well, and it's uncertain, the investment won't happen. So I think that's how it will. I don't want to say this get to 100% would take care of itself, but it's about time. How fast can we do this? And the biggest hurdle I see at the moment is if we don't have the networks ready to run, inverter-based only, so we don't need to have large rotating machinery and keeping coal plants at minimum loads and all this sort of stuff. If we don't make that transition happen fast, people will sit on the fence on the side and say, well, I can't really connect and invest and do things because I've got to wait first for that to be resolved. Once it's resolved, I think it will unravel itself, so to speak. And look, these days, through digitalization and the ability to work much faster, much better, I think the speed of change we see coming up. I use the example how long it took, say, for wind turbines to become down in price and be, mainstream. That was probably, say, 20 years. Solar PV took, 10 years, 15 years. Battery energy storage, much faster now. And I think come back to hydrogen will even happen to a certain extent faster, but very different drivers compared to what we've seen before. So yeah, stabilize first, create a network that's able to connect all these different sources and then store.
That's the foundation for the house, sounds like, right there. Stabilize the network first.
Yes, because if it falls over and if blackouts occur, everyone goes back in the hole and everyone says, I told you so. It shouldn't have happened. Not going to work. So we have a huge responsibility to get this right. And we have an opportunity to get it right, and we need to get it right. But yeah, I think that's our task at the moment. But afterwards, it's an energy equation that then gets solved.
And just to extend what Juergen said, specifically, we have the technology that can make it happen. But technology is out there. It's ready. You just need to use it. It needs to have a way to market. It needs to have a way. Yeah, go ahead.
Yeah, and one thing I forgot, PKD to mention in this, how to get 100%, is this also now what's happening now is the intercontinental connections, right? So if you Google a name called Sun Cable, so this is the company in Australia that's proposing to connect now 20 gigawatts of solar from the central of Australia into Singapore, into Indonesia through HVDC cables. And one can see, of course, why that will decouple this dependency on the sun only shines during the day and all this sort of stuff. So once it's a bit like the internet, right, where we're interconnecting, of course, between continents. And that's the whole idea of, well, you start to interconnect between, countries or continents, like it happens in Europe a lot. And I'm sure you've got that too. But then to decouple this demand versus the load, or generation versus the load, to make that equalize better too.
Well, there's never been a more fun or interesting time for those of us who want to,
yeah.
figure.
You want to get in the
out.
industry? Now is the time. Yes, absolutely.
Yeah.
This is you can make a big difference now. I mean, this is again one of the things will be constrained by supply chain and people, right? I mean, that's the biggest thing, right? Now, how can we make this all happen? Because this is not just pressing a button, make more of the same. You will need people, you need engineers, you need business analysts, all sort of, creative, innovative people to make this transition happen. And time is the essence now. So to me, if I would start again, I'll be definitely encouraging. And I say to my son as well, now's a good time to get into this because it's going to be there for quite a while.
Yeah, the electron's never been more interesting than it is now.
Yeah, absolutely. And one thing is always good, regulation changes, prime ministers change, policies change, but the physics stay the same. So that's one thing I always say. One thing you can rely on is that the physics stay the same, no matter if it's 50 hertz or 60 hertz. But, at least the principles remain the same. And that's why this is transferable, what we're talking about now. Your power system, even though it runs a little bit faster, at the end of the day, operates on the same physics that we used to.
John, last words from you around lessons learned?
For me, I look to Australia for leadership around this area because they've put in more renewables into networks where they've reached these really, really high penetrations sooner than most of the rest of the globe has. This is an extension of what happened in remote areas 15, 20 years ago and into about up until even today. And as you see this, you take off chunks, increasingly large networks are getting to the point where they have to start thinking about some of these issues that technology can solve. And Australia is just at that nexus where it's got scale, it's got renewables, it's got a common level of development, it's got money that it can invest into this problem. We can learn a lot by looking at them and replicating some of the successes and avoiding some of the mistakes that they may have made. It's just it's a really exciting time, and there's a lot to be learned from what everybody's doing globally.
Thank you. And Juergen, last words.
Yeah. Look, this is more personal note of encouragement to say, never give up, right? I mean, there's a lot of naysayers out there that say it doesn't work, you can't do it, all this sort of stuff. Stand up, believe and put out there what you think is the right way to go. And you will succeed. I mean, that's my lesson learned over many, many years, that if you've got the right technology and you've got a genuine reason to promote this and put it out there, I do believe over time you will see change. So yeah, make sure you're part of the change, push hard, and we'll make the transition happen.
Well, thanks. It's pretty clear that we will continue to have a lot to learn if we continue to look south to see what's happening in Australia. Well, thank you all for joining us. And again, we'll hope to see you next month at the next Pick My Brain session.
Thank you all. Thank you, PKD.
Thank you. Good stuff.